For years, the James Webb Space Telescope has felt like the final word in space astronomy. With its enormous mirror, unprecedented sensitivity, and breathtaking images reaching back to the dawn of the universe, it gave humanity the impression that we had finally built the ultimate eye in space. But now NASA is preparing a new observatory that changes the game in an entirely different way. Instead of looking deeper into one tiny patch of sky, it will scan vast regions of the cosmos with incredible speed, allowing scientists to measure the shape of the universe itself. This new telescope is not designed to replace Webb. Instead, it is built to reveal everything Webb was never intended to study: the invisible mass that binds galaxies together, the mysterious force driving the universe apart, and the hidden 95% of reality that science still cannot explain. Once it begins its mission, astronomy may shift from asking what a single galaxy looks like to asking what billions of galaxies are doing together. On paper, NASA's new observatory does not appear to be the obvious successor to James Webb. Its primary mirror measures 2.4 meters across, placing it in the same class as the Hubble Space Telescope and making it much smaller than Webb's massive 6.5-meter mirror. Judging only by mirror size, it might seem like a step backwards. But that assumption misses the true purpose of the telescope. Its greatest strength is not simply seeing deeper, it is seeing wider. Unlike Webb, this observatory has a field of view roughly 100 times larger. A single image can capture an enormous section of the sky that would require nearly 100 separate observations with Webb. One telescope functions like a powerful microscope, while the other operates as a wide-angle survey machine for the cosmos. Webb can reveal astonishing detail within a single galaxy, but the Nancy Grace Roman Space Telescope can show what billions of galaxies are doing across space and time. That distinction is more important than most people realize because the greatest mysteries of cosmology cannot be solved by studying one object at a time. To understand dark matter, dark energy, and the large-scale structure of the universe, scientists need enormous statistical datasets. They need to observe huge numbers of galaxies spread across immense distances. They need breadth as much as depth. That is exactly what the Roman Space Telescope was built to provide. It is not trying to outperform Webb at what Webb already does exceptionally well. Instead, it is performing an entirely different scientific mission, one that Webb was never designed to accomplish. The real reason this telescope matters so much lies in one astonishing fact. Everything humanity has ever seen, touched, built, breathed, or studied, every star, planet, galaxy, and atom of ordinary matter, accounts for only about 5% of the universe. The remaining 95% consists of dark matter and dark energy, invisible components that dominate the cosmos while remaining among the greatest unsolved mysteries in modern physics. Dark matter reveals its presence through gravity. Galaxies rotate so rapidly that their visible matter alone cannot generate enough gravitational force to keep them intact. The stars at their outer edges should be flung into space, yet they remain bound together. Something invisible is supplying the missing gravity. Dark energy is even more mysterious. It appears to be driving the accelerating expansion of the universe itself, causing space to stretch faster and faster as billions of years pass. Scientists know these phenomena are real because their effects can be measured with extraordinary precision. What they actually are, however, remains unknown. This is where the Roman Space Telescope becomes so scientifically exciting. Roman was engineered specifically to measure these invisible forces by observing their effects on light and cosmic structure with unprecedented accuracy. Rather than merely inferring their existence, it will map their influence across enormous portions of the universe. Roman is not simply another telescope built to produce beautiful astronomical photographs. It is a scientific instrument designed to reveal what cannot be seen by carefully measuring how invisible forces distort everything around them. Its most powerful tool is gravitational lensing. According to Einstein's theory of general relativity, mass bends the fabric of spacetime, and light follows those curves. Even though dark matter cannot be observed directly, its gravity still warps the light traveling from distant galaxies behind it. Those galaxies appear slightly stretched, distorted, or aligned in ways that would not occur if no hidden mass existed. Studying only a small number of galaxies provides intriguing hints. Studying billions produces an extraordinarily detailed map. The Roman Space Telescope is expected to measure gravitational lensing across roughly 2 billion galaxies. That represents a dramatic leap beyond previous surveys, which analyzed only tens of millions. With such an immense dataset, the subtle signal of dark matter becomes impossible to ignore. Roman will create the first enormous three-dimensional maps of dark matter spanning vast cosmological volumes. At the same time, it will measure the universe's expansion history over approximately 10 billion years by observing distant supernovae and the large-scale distribution of galaxies. This means Roman will not only reveal where dark matter exists, but also test whether dark energy behaves exactly as Einstein's cosmological constant predicts, or whether entirely new physics is at work. In other words, the telescope could determine whether the universe's accelerating expansion is relatively simple or whether it points toward revolutionary discoveries hidden just beyond our current understanding. As remarkable as its Dark Universe mission is, it represents only one part of Roman's scientific potential. Simultaneously, the telescope will monitor nearly 100 million stars in the dense central region of our galaxy, searching for tiny brightening events known as gravitational microlensing. These brief flashes occur when a foreground object bends and magnifies the light of a more distant background star. If that foreground object possesses a planet, the planet leaves its own distinctive secondary signature within the light curve.